So thanks very much, Alex and Ya, for inviting me to this nice tutorial. So I'd be very happy to talk here. So today I'm going to talk about fair division of household chores. So this is a joint work with NPO called Code for Japan and a PhD student in the University of Tokyo, Tomohiko Yokoyama. So let me first give you some background of household chore division. So as many of you might experience, household chore division can be a great source of conflict, especially there's a gender gap. So there's a tendency for women to spend more time than men on household chores. And often inequality in the division of household chore can cause many problems, such as like causing significant stress and so on. And people often say that there is no way to discuss with their partner what chores they can do, or they might also complain that their partner does some routine work, but they are not aware of other kind of invisible chores. So relatively recently, we have developed a household chore division app based on the theory of fair division. So this is a communication tool for couples, not for fighting. And what we do is pretty simple. So in our app, what we do is based on the preference of the user, we visualize the current allocation and propose a suggestion that is fair and efficient allocation. And we have made this app together with NPO called Code for Japan. This is a kind of organization to promote civic technology where more than 5,000 engineers and designers have been registered. And this activity actually has appeared on a TV program of a major Japanese broadcasting company called NHK on 29th of May 2022, so almost 3 years ago. And it has had some social impact. So it has attracted more than 10,000 users within the first month. And so this is, I mean, you can see, like, I mean, these are the screenshots of the TV programs, and then you can see me at the right bottom corner explaining how complex household chore division can be. So coming back to our question, the question we want to solve is how to fairly divide chores. So if you know, I mean, if you are not familiar with fair division, you might think that maybe this problem is easy. You can just kind of allocate the set of chores equally among the participants. But here we may have different kinds of chores. So we may have heterogeneous preferences. So meaning that some people might prefer cooking over cleaning, or others might prefer maybe the other way around. And in this case, the question of how to fairly divide chores becomes a tricky problem. And so our question is, I mean, how to fairly divide chores when people have different preferences. When people have different preferences, so people might prefer cooking over cleaning and so on. So as many of you might know, fair division is a growing field of mathematics and computer science that provides an elegant answer to these questions. As you will see in the latter part of the tutorial, it has been applied in many applications, including split and course math, so the allocation of courses among students, or the allocation of the rent among roommates, and so on. So in today's talk, I would like to share my experience of applying fair division to this specific application of household chore division. And part of this, so I'd like to note that this app has actually appeared as a demo track, as a demo paper at AAA 2023. So you can refer to this paper about, how we designed the app and what kind of algorithm we have used in this app. Okay, so this is the basic kind of background. So let me proceed with the model. So the model we have used is quite simple. So we have a set of agents and we have a set of indivisible items. And we assume agents have additive utilities. So since we want to divide shards, agents can assign kind of negative utilities to each of the shards. And the utility for each combination of the shard is just simply the sum of these utilities. Okay. And our goal is to find allocation that is fair and efficient. And by fairness, we consider MB freeness. So allocation is considered to be fair if for any pair of agents, the utility I can derive from my bundle is at least the utility I can derive from the other's bundle. But since we are dealing with indivisible shards, so since we are dealing with discrete items, we cannot really guarantee the existence of MB-free allocation. So we may look for approximation of MB freeness called MB freeness up to one shard. So for any pair of agents, you don't MB others, or there exists at least one item in my bundle whose removal eliminates the MB. Okay. So we also want to consider, not only fairness, but also efficiency, because achieving MB freeness is not enough in practice. So there might be a better reallocation that makes everyone much happier. And as an efficiency notion, we consider Pareto optimality, so meaning that there is no reallocation that makes everyone weakly better off and some strictly happier. So the main theoretical questions in recent years is that whether we can achieve both fairness and efficiency in this discrete setting. And here are some kind of well-known facts about fairness and efficiency in the discrete item allocation. So for non-negative additive utilities, we can achieve this EF1 and PO by maximizing the product of utilities. So for goods, we can achieve, these two properties of efficiency and fairness. But for shards, this is a major open problem. We do not know whether EF1 and Pareto optimality are compatible for shards. But for the case of household shard division, which means that for the case when there are two people, we have a nice, elegant algorithm for achieving EF1 and Pareto optimality. So this is actually the algorithm we have used in the app called adjusted winner. So this adjusted winner is originally designed as a protocol for divisible goods and two agents. And it is known that if we discretize the protocol, then the discrete version achieves this approximate notion of MB freeness and Pareto optimality. And the idea of this adjusted winner protocol is quite simple. So we have some tentative loser and then tentative winner. And we initially allocate all the shards to the loser. And so this allocation is very kind of unfair but efficient. And then along the Pareto frontier, we may eliminate MB step by step. So what we do is that we sort the items in terms of the disutility ratio. So on the left, you have some shards that are more kind of heavier for the losers, that are hated more by the loser. And then on the right, you have shards that are kind of heavier for the winner. And then we are going to transfer one item step by step until we reach an EF1 allocation. And by doing this, we can keep Pareto optimality while kind of reducing MB step by step. And this is a way to achieve Pareto optimality and EF1 for the case of two agents with negative utilities. Okay. So this is kind of bit like brief background of our theoretical model. And what we do in this app is that based on this theory of fair division, we have developed this household short division app. So this is kind of the interface of the app, and you can see that again, what we do is pretty simple. So based on the preference of the user, we visualize the current allocation and propose a suggestion that is fair and efficient, which means that EF1 and Pareto optimal. Okay, so let me explain how the app looks like. So the couples first selects a set of chores to be divided. So something like making breakfast or grocery shopping and so on. And then they are going to enter the current chore allocation. So if they do, if they believe they do, they make breakfast. They say yes to this answer, and then if they don't, then they say no to this to each of the questions. And then we want to kind of elicit the utilities agent may have for each of the chores. But since the concept of utilities is a bit difficult to explain to non-experts, in this app we decompose the meaning of utilities into two. So these three-level preferences. So for each of the chores, we ask users to express whether they are positive or negative or neutral about the chores. And for each of the chores, we also ask, how long it takes time to complete each of the chores. And in our calculation, the disutilities is given by this time times the three-level preferences. And now, based on this, we visualize the current allocation. So this pie chart depicts the allocation from each user's perspective. So this colored region is the disutility of the first user, and so this red region is the disutility of the first user. So the disutility this agent experiences in their allocation. So she or he's kind of envying a lot because they are getting more than half.
Yumi, a short question. How do you
Okay.
how do you encode chores that are shared? So I'm looking, let's say, a check mail, right? I don't think that there is one person in our household, at least, that is in charge of checking the mail. Like, I'm kind of like check it when I arrive home. I open the mailbox, I take it out, and I come upstairs, or whenever, or it's my wife who does it, or my kids sometimes. So it's like depending on that. And similarly for making dinner, like in some days I do it, some days my wife does it. So how do you encode stuff?
So in this very initial version, we assume that they don't share. But in the most updated version, we ask frequency. So how many times
Right.
each user does each of the chores.
Got it. Thank you.
Yeah, thanks for the question. Okay, so anyway, so this is our app, and then on the right column, you can see the proposal, the allocation suggested by the adjusted winner. And we have also additional features that since, we cannot maybe incorporate some of the constraints user may have, people can customize the allocation by clicking icons of the chores. So maybe there's a question. Okay, sorry, let me take it later. So I think okay. So this is how we calculate the disutilities. So this utilities is basically given by the time times the three-level preferences. So this is the overview of the app. And so now you might think that whether fair division really helps. So we have a very nice theory of fair division, and then you might wonder with how people actually think about our fair allocation. So we have collected some data, and our first observation is that according to our metrics, according to the way we calculate these utilities, actually the solution proposed by adjusted winner decrease this utility users may have and reduce envy. We have also, but this does not mean that users, this does not mean that users really feel the proposal made by adjusted winner is fair. So we have also some kind of, answer to these questions. So we have, when we appeared on TV, we have collected more than 100 answers to our questionnaire about users' satisfactions. And about 60% of the answer find the app useful as a communication tool. But in terms of fairness, we don't really have a satisfying answer. So I'll go in the remaining time, I will go a bit into the details. So let me show you some.
Ayumi,
Okay.
I think there's a question online and also a question.
Okay.
So online, Christian asks, do users have incentives to be truthful?
Okay. I see. So let me see. Okay. So
And then
yes. So no. So to this answer, to this question, I would say no. So adjusted winner is not strategy proof. So people can misreport and benefit from the misreport. Although I'm not sure whether the actual users are trying to kind of play a game.
If you're lying to your partner on the chore division app, I feel like you have bigger problems than chore division in your relationship. But that's just my perspective.
Right. Yes.
Although if it's
and
romance, then I can see it happening, like, if it's not your romantic partner, but just some like your roommate, and you're like, whatever, I lie.
Right. So,
There's also
but
a question from Nisarg on the chat, Ayumi. So in
okay,
how many of the 829 instances were you able to find a Pareto improvement?
I see. So, that we didn't check. Sorry, so I cannot really answer this question. So I should have checked. Sorry, but maybe.
Sorry.
Okay,
Go
so
ahead.
let me show you the data.
Just in the last question, in the just winner procedure, does it matter who gets the initial allocation, endowment? Is it a different outcome?
Sorry, can you say it again?
So in the just winner, you give one all the chores, and then you start giving the other one some chores according to this
Right.
portion. Does it matter who
Right.
gets them first, or is it the same outcome?
Right. So it matters, right? So usually, so adjusted winner tends to assign more chores to the loser. So if you are selected as the loser, then you may get more chores. So what we do in the app is we just randomize between the losers and the winner, so that the same person cannot, we don't allocate too much to the same person.
And there are a couple more questions or comments. One is Nisaj said he was referring to a point in the previous slide that you said that you were able to reduce this utility for both users.
Right. So let me maybe explain to this slide. So
Okay.
this is so this shows kind of the fraction of people having each range of the disutilities. So in the above you can see, so there in this app we have two agents. the first agent who enters the preference and the current allocation, and then the second agent who enters the second. And so this is on the left, this is the fraction of the first agent, the first type agent who have varying degree of disutilities, I mean, varying degree of normalized utility. So for example, in this green part, 44% of people having this utility, I mean, normalized this utility of 0.5 to 0.6. So this means that, I mean, in this current allocation, roughly 30% of the users are kind of MB-free. And on the left, we have the second type of agent, and roughly here, 50% of the agents are MB-free and the current allocation. So, so these are just their current allocations. So we don't know how they divide the shorts. So, so this is the proposal made by the adjusted winner. So we consider, we look at the fraction of people who are MB-free and the proposed allocation by the adjusted winner. And you can see that we make more, I mean, roughly twice as many people MB-free if we use by using adjusted winner allocation for the first type of users. And also we also increase the fraction of MB-free agents in the second type of agents have also increased from maybe 50 to, I mean, maybe 70%. Okay. So that might partly answer the question. So, so you can see that, I mean, if we use, I mean, according to, I mean, there might be some discussion about how we model this problem, but according to our metric of these utilities, you can see that adjusted winner indeed makes things fairer than people's, I mean, users' daily allocations. Okay. So let me also show you some feedback from the users. So we have, we ask, so as I said, I mean, many people find our app useful as a communication tool because people can learn about the preferences of the partners, which they might not be aware of. And but in terms of fairness, people have different ideas about what fairness means. So when we ask whether they find a proposed allocation fair or not, actually about half of the people says they are not sure. And also for those who said yes, they are kind of, I mean, people have different reasons for why they think a proposed allocation fair. And maybe, I mean, this is really a small survey, but here in 50% of the people think that they think the proposal is fair because adjusted winner indeed Pareto improves their current allocation. So it was useful as a kind of negotiation tool. Okay, so sorry, I'm running a bit late. So so this is our app, and then if you are interested in, please use it, the kind of English version and Japanese version. And then I think our app inspires several interesting future directions. So thank you very much.
Thank you very much, Ayumi.
Ayumi.
It's very interesting. I have so many questions. I mean, every time I've listened to you give this talk several times, and every time I have like a million new questions about it because it's so interesting. But I feel like we have Alex will be starting. Maybe we have time for one very quick question from the audience while Alex shares his screen and sets up.
I think there was one in the chat that we haven't answered. Wishwa says, I see that the website currently shows two options, one slightly fair allocations and two fair allocations. I'm guessing two is EF1 plus PO. What is slightly fair allocations?
Right. So yeah, sorry, I didn't explain that part. So this is an allocation which makes a minimal modification to their current allocation. So we are trying to find a best transfer from the embed users to the MBS users to embed user. So since we believe that often people cannot really change their routine work, so I mean, we have to suggest something that is closer to their current allocation, but that is fairer than the current allocation.
That's great. Thank you.
Thank you. Very interesting. All right. I'm very pleased to introduce our next speaker, who's going to bring us from the world of allocating chores to a refugee resettlement. We have Alex Teytelboym, who's a professor at the University of Oxford, Department of Economics. And thank you, Alex, for joining us today.
It's a huge pleasure to be here. I hope you can see the slides and you can hear me. And yeah, and Alex, thank you so much for inviting me. So this is going to be a super fast talk. I'm not quite a match kind of Ayumi's elegance, but it's going to be about these. It's been a huge project trying to figure out ways of making refugees' lives a bit better. And I want to discuss a couple of them. They're not going to be as theoretically elegant, but I hope they will. I've highlighted the word practice, and so they're mainly going to be kind of about the practice of how the theory has informed the practice of refugee resettlement. And it's been a project with many people. Wonderful, and we are great friends. So this is the situation we're in right now. Is there's a guy in the US who gets to decide how many refugees come to the United States. United States is one of the biggest recipients of refugees in the world. And what I mean by recipients of refugees, I mean people who come through a kind of a centralized process, essentially governed by the UN. There's a lot of refugee movements that are irregular. This is a very regular scheme, but unfortunately, the president of the United States has the control over the numbers, and the current president has stopped refugee admissions indefinitely. It's being challenged in the courts at the moment, but it's a very bleak situation. So let me tell you about sort of how it happens in a normal year before this current administration came in. When refugees come to the US, they basically go all over the country, and they go to typically they go to places that are very big, like Texas and California and Florida and New York State. And the only place you can see kind of not colored in here is the state of Wyoming, which is beautiful, but for some reason it wasn't getting a lot of resettlement. And what we're interested in is essentially allocating people to places where they can thrive. So just to give you kind of a brief overview of how this whole thing works, thousands of people arrive to the US every normal year, and we are not in a normal year. So since 1980, roughly, when the scheme began, about 50 to 80,000 people would arrive every year from different countries around the world and be on path to becoming US citizens. And the process is governed by what are called resettlement agencies. The US government basically just does security clearing, and then they hand over these refugees to resettlement agencies. And we work with one of them called FIAS. And the thing that is key is that the initial match of the refugee and the location really matters for their outcomes. This has been documented in many places around the world. It's not just that some places are better at helping refugees thrive. It's just some places are better for certain kinds of refugee families in terms of helping them thrive. And that's what makes this an interesting allocation problem. Who should go where, given some particular objective? But the resources are very limited. These resettlement agencies are NGOs. They get a bit of government funding. They have some money that they raise themselves, and so there is a kind of capacity constraints. The capacity constraints are actually mandated by the U.S. government. So, for example, if I want to resettle 50 people in West Lafayette, Indiana, then I'm going to make a commitment. I will tell the U.S. government, and I will have to stick to that number. I can't do any more than that. If I do less, I also get told off. So you really kind of have to try and make sure you kind of get to your quota. So how do we improve the outcomes under this kind of thing? And the thing that makes the entire thing very difficult you can't have a complete control of the process. What you can do is create software that basically guides the allocation process. But in the end, the resettlement agency has all the control over what's going on. And so I want to tell you a little bit about how we sort of tackled this problem. So we had a kind of a first paper about this, introducing this software, which is called Anymore. I'll show you why later on. And it works in a very simple way. You can get data on past employment of refugees from the past. You deploy a bit of machine learning and econometrics to essentially learn the probability that a particular refugee gets a job in a particular area. And then you marry it with a bunch of integer constraints that essentially incorporate various needs and services that are provided at a local level. For example, the refugee family might come in, nobody might be able to speak English, but they might be able, maybe they're coming from Syria, they would speak Arabic, but there will be an Arabic translator in that particular affiliate, if you like, a location where the people will be going. So that would be a good match. And if in fact there is nobody who speaks Arabic there, then maybe we wouldn't match people there. And there's a bunch of constraints like that. Some of them are to do with medical issues, language, etc. So you put in all of these kind of service constraints, and they are, data again that you can get from the affiliates, these kind of local NGOs themselves, and you use some integer optimization software, and boom, you get an allocation. It's just an integer. An integer programming problem, and if your objective is to maximize employment outcome, and that's what you observe in your data, then indeed you can have a suggested match that's going to tell you where you should place different refugees to maximize this allocation. Now, to maximize this objective. Now, just to repeat again, the matches are suggestive, and so you can suggest them to the agency, but in fact, what we found is that the agency, by and large, follows what our software has suggested, has been suggesting to them over many years now. Now, this is the kind of very simplistic model, right? I'm going to make it a little bit more interesting, but just to kind of fix ideas. If all the refugees arrived at once and we had all this data and, you could do these estimates properly, it's just a simple maximization problem. So this turns out on its own, if you just sort of run numbers on this, you can boost employment from something like 30% of refugees getting a job within 3 months of arrival to something like 40% of refugees getting a job within 3 months of arrival, while completely eliminating all the bad mismatches you can have because of medical issues, etc. So while you're actually making the kind of, if you like, the matches better in the sense of their better fits, you can also at the same time increase employment by 30% or 10 percentage points. So that's cool, but let me show you how much more complicated the problem actually is. And the problem is complicated, and we highlighted this in our more recent work that came out. This is the 2.0 version of the software. The reason why the problem is complicated is because refugees arrive over time. And so I just want to walk you through an example of kind of what's the difficulty in a static versus a dynamic problem. There's many people on this call, I can imagine, who have studied online matching problems. So I apologize if this is a little bit too simplistic, but I just want to kind of get people to sort of see what the key trade-offs are. So imagine we had two locations, Austin, Boston, and Austin had a capacity to host 5 refugees, and Boston had a capacity to host 5 refugees, and there were basically 3 families. The first one has 3 members, the second one has 1 member, and the last one has 2 members. And then these edges colored in a way that suggests that the employment is good versus bad. Green means really good employment, bad means the employment outcome would not be very good. And so we can do the thing that we did just before. We've got capacities, we've got these employment scores, let's do some integer optimization. And maybe what it tells us is that, look, you should match the top and the bottom family to Austin, and you should match the middle family to Boston. And most of the edges are kind of green, and so you can hopefully trust me that that would have been the solution, right? Now, note this really depends on the fact that the problem is static, so all refugees arrive at once, and they just don't. They arrive over the course of the year. Let's now see what might happen if you sort of myopically optimized. So let's say the first two families show up, and you look at how well they can do. And what you can see here is that both families are much more likely to get employment in Austin relative to Boston. So myopically, you might say, look, let's just, locate them into Austin. Great, they've arrived. Let's maximize employment. We've got space for 4 people in Austin. This is really good. So you do that and you allocate the 2 families to Austin. And now the capacity in Austin has been reduced by 4. So from 5, it becomes 1. But then the last family shows up. And remember what we said before, the optimal solution was actually not allocating the first and the second family to Austin. It was actually allocating the first and the third family. And had we waited a little bit longer for that family to arrive, we could have allocated them to Austin. But instead, now we don't have a choice. We have to allocate them to Boston. And essentially, that's suboptimal. And so if you do this kind of myopic matching, very intuitively, what you're doing is you're just kind of favoring people who are arriving early, which is a bit arbitrary. The fiscal year in this world runs from beginning of October to the end of September. And so, if you happen to arrive in October, you lucked out because there's going to be a lot of capacity in a lot of great areas. And a lot of areas are good at providing employment opportunities for different types of refugees. So it might just be easier to get better matches at that time. Now, again, you might say, well, why don't you just kind of adjust the capacities to take into account in some proportional way? And I am saying, no, even if you adjusted the capacities in a kind of proportional way, this, you're going to kind of face problems. So here is a picture, which is, I hope, kind of very helpful if we just stare at it all for a bit. If you order all the refugees in the order of arrival, left to right, like imagine people are coming over time. So on the x-axis, you have time or order of arrival. The optimal policy would basically disadvantage refugees who are arriving earlier relative to a greedy policy that would just try and pack as much employment as quickly as possible. And the reason is that the optimal policy, the one that knows exactly who's going to arrive and when, is going to hold back some capacity early on to use it up on the best possible refugees later on in the year, right? And so the greedy policy is greedy, and so it uses up all the best capacity. For example, a place like Pittsburgh is unbelievably good at providing employment opportunities. It might use up a lot of the capacity in Pittsburgh, and so refugees who are coming in later on are going to have a much lower average score. And so what really happens, you're sort of trading off this slightly better matches earlier on in the year versus much worse matches that are going to come later on. And instead, you should do the opposite. You should be patient. You should hold back the capacity and then use it better later on. And the loss is substantial, as I'll show you. You actually do. There's quite a bit of loss on the order of about 10%. Alon, you have a question?
Yes. Do you assume anything about the arrival order, like worst case, random?
So I'll show you. So we assume that the arrivals are basically going to be governed by a process that is it's stochastic, but it's quite easy to predict roughly the composition. So we build a model that sort of says, this is the number of people we expect to get from different demographics in the next few months. That can vary, of course, because there might be structural breaks. Trump comes in, we stop all Iranians, for example. So you have to manually sometimes adjust these things. But you do need a kind of some prediction. And the key thing that really makes a difference to this model specifically, it's not so much the demographics, it's really the number of people who are going to be arriving. That's the thing that you really need to have a good idea about. But that seems to be quite easy to predict if you just look back sort of 6 months from before. So in other words, if you sort of saw the way you want to use up capacity is kind of like this blue line on the bottom is very, very gentle over time, rather than using it up very aggressively at the beginning and then kind of running out of spaces later on. So how do we do it? In a way, it's a very naive method. It just seems to work incredibly well, and we only later discovered why that was the case, thanks to some wonderful work by Sid Banerjee and others. the way to kind of think about it is when you place some refugee in some affiliate, two things basically happen to this refugee. Well, it increases employment, right? Because this refugee is going to get a job. But at the same time, what it does is that there is an opportunity cost. It's going to take up a slot of somebody else who could have come later. And the key thing to do is to recognize that there is this opportunity cost. That's the key thing that you want to do relative to the greedy policy. So you can estimate this opportunity cost by, like I was suggesting, you simulate the future arrivals, and then you optimize for this kind of simulated trajectory. So how do we do it? We impose a shadow price on each location, and it's kind of supposed to intuitively capture this opportunity cost of using up some particular unit of capacity. So if a particular place is really good at giving refugees jobs, there's going to have a high shadow price because taking up a place there might actually be very costly. So you need to be really good at getting employment, according to our model, in order to be able to have a good chance of being placed there. And so rather than maximizing employment, maximize employment minus the opportunity cost, just take into account the cost. So it's a kind of pretty easy thing. It's very easy to implement because you're doing this myopically. But it turns out that this is a kind of a special case of some much broader ideas that Sid Banerjee has been developing that calls the Bayesian profit. So great work. I advertise it and recommend it to you all. And we turn out to kind of be using a kind of a particular instance of this. So with this pricing approach, what would happen in our example is that we would look at the second person who was supposed to be arriving and say, hey, actually Austin is really popular. A lot of refugees can get employment there. We're not going to allocate you to Austin. Instead, we're going to allocate you to Boston when you arrive. And that will hold back the capacity for the third family that's going to be able to get employment there later. Now, this turns out to work scarily well, I would say. So if you compare this pricing-based purple approach to the optimal hindsight, that is, you know absolutely everything, sort of like God, exactly who's going to arrive and when, you almost perfectly trace out the optimal hindsight trajectory, and you get within, I'll show you in a moment, within a kind of percentage point of the optimal solution. And you can see that it looks very, very similar. This sort of slow and gradual use up of capacity seems to work very, very well. And so if you compare this across different years, you find that the purple bar, by the way, it's the one that's we are suggesting that we've deployed. And it's within a couple of percentage points within what is the optimal hindsight that you would expect to get. Now, created the software for the agency to make it as easy for them to use as possible. And what happens is that you have a sort of a little screen like this. Each little box represents a family, and there's some data on them. So the color-coded boxes are basically families. They're called cases, and they're color-coded according to essentially their overall score, if you like, their net contribution, the employment minus the opportunity cost for each case. And the blue boxes are the ones, they're the affiliates. So each of these will have multiple families. The software basically suggests a particular allocation and says, this is what we think you should do. And the arrivals officer is able to move these boxes around and see what impact it's going to have on the actual employment. And so they have complete discretion. But actually what we see happening in practice is that they basically typically accept our recommendations and end up spending most of the time dealing with really difficult to place families, which is where really kind of it's very hard to remove the human from, very hard to automate. And the arrivals officer spends with people who have severe medical conditions or people who maybe have large families where there's a lot of kind of very complicated constraints. And that's actually their expertise. That's what they wanted to do is dealing with extremely kind of complicated, vulnerable cases. So what's great about the software is that it keeps, allows us humans to specialize on what the human's good at and does the kind of grind of this allocation while keeping that employment objective in mind. And I should have said that this employment objective is in fact mandated to the agencies by the US government. So we didn't choose to maximize employment within 3 months, which is quite an odd objective if you think about it. But unfortunately, or fortunately, or whatever, it is just the case in the US that the agencies are mandated to maximize their objectives. So we're very much going to have to, take that objective on. I horrendously mistimed. I was planning to tell you about another project, but I've run out of time. So in a way, this is kind of ideal, right? I am perfectly on time, but halfway through my talk.
No, this was extremely interesting, I have to say. It's really cool.
Yeah, thanks,
Um,
Alan.
The
There's a question in the
question,
chat. Yeah.
But what is the question? Let me just see.
I have a question about
Great. So there's a question about kind of so what happens is that the families apply through the UN, and then they get allocated to the United States. Eventually, they apply from a refugee camp temporarily to the UN. The UN has a screening process which looks for the most vulnerable refugees that really need resettlement. The number of these spots for these people is tiny compared to the kind of overall demand, like an order of magnitude less than the demand for these kinds of places. Then the UN basically says you're vulnerable enough, we're going to allocate you to a country. Then your case gets picked up by the US. Then the US has a process of allocating each case essentially at random to one of the resettlement agency. And then we see it in our data, and we actually get to allocate this family to, say, Pittsburgh or West Lafayette, Indiana. Or I should have said somewhere pleasant in Massachusetts, right? Sorry, yeah, I should have used your example too.
I have another. Does it make sense to deploy such a system in the EU? Have you thought about
So yes and no. We've talked. It's much easier to solve things at a level of an NGO than at a level of a multinational organization like the EU. The EU is, kind of remarkable in many ways in how they deal with these issues, but it is very hard to kind of use it at a kind of international level. We have thought about, and we've thought about using it within an entire country where often processes are centralized. Germany, you could do it within a particular federal state, you could do it across federal state. In principle, as most of you imagine, it doesn't really matter what the scale is. The question is, do you have data? Do you have institutional support? Do you have some ability to actually implement this allocation? That's where it turned out to be quite much easier to work with a resettlement agency in the US. There are some people on this call, like Vahida, who's talked to other agencies in the US. They're very autonomous. They kind of work together, but in some sense separately, because they get their refugees directly from the State Department.
I think that it is a good time to pause because we don't want to be too over the schedule.
Yep.
But thank you, Alex. Really fascinating and important work. I think that applying tools for market design for the common good. I mean, this is really wonderful.
Yeah.
So thank you.